Alright, kiddo. So in this video, what I want to do is now that we have kind of this general idea of what the extreme value theorem is and what it says, I want to show you how we can get and find those extreme values. And not only find them, because our calculator can do those for us, but verify using calculus that those are indeed extreme values. So recall that the extreme value theorem just guarantees that as long as we have a function that's continuous, right, which is a polynomial, on a closed interval, so from -1 to 2, then there has to be a min, there has to be a max, right? There has to be a highest and lowest point of any function as long as it's well behaved on a closed interval, as long as it's continuous. So that's the extreme value theorem, but we got to go out and work to find them. One way to not go out and work and find them is to just use a calculator, saying calc max and min. It's something a calculus can do for you. But there is some good calculus theory behind that sort of max-min finding that I want to go through right now. So here we go. We talked about how we can use a derivative. So recall that derivative is positive means the function is increasing. Derivative is negative means the function is decreasing. And when the derivative equals 0, we have horizontal tangents. So what we're going to do is we're going to take a look at this function here. And you can see what's going on here. We have a nice quartic, right? So it's an even degreed polynomial. It has up and up. It has the same end behavior. So what we're really trying to do is hone in on from -1 right around here all the way up to +2, right? So we're looking at a window, an x value, an interval over which the function is continuous, and we want to find the min and max value. Okay? It appears, or fairly obvious, that this value right here, the valley, that's going to be the minimum value, right? So we have to find out where that is using the calculus. And the maximum value is probably going to be up here at one of the endpoints, either at -1 or over here at 2. Probably at 2, it looks like. Right? So what we're first going to do is we're going to use the calculus and the derivative to find what we call critical points. So critical points are where something interesting happens, namely the derivative equals 0, or later where the derivative doesn't exist, but we won't get into that now. So I want to find the horizontal tangent. So based on what I'm looking at here, there's going to be two horizontal tangents. It looks like one at 0 and one at whatever that x value is. And that's what we want, for the minimum at least. So let's get the derivative, and that's easy enough to do. So the derivative using the power and coefficient rule is going to be 12x cubed minus 12x squared. This is a nice easy one. We'll start easy. And I can factor, just so algebraically it might make a little more sense. Right, and so that's really what I'm looking at, the derivative. So what we're going to do now is I'm going to actually graph the derivative as well on the same graph. So let's see if we can do that. So I'm going to use my handy dandy TI or Inspire. Go to menu. I'm sure there's an easier way to do this. And I'm going to add the graph of its derivative, which is 12x cubed minus 12x squared. And again, I just have it in factored form because we'll mess around with it later, right? And so I want to graph that, and there it is in red, okay? So later, what we're going to do is we're going to kind of make connections between, a function graphically and its derivative. But for now, we'll kind of leave them both sitting up there for you to take a gander, right? So the red is a derivative of the blue. Fair enough? What we want to do is we want to find out when the heck the derivative equals 0. So the critical points, I'll call them CPs, those are points at which we might very well have max or min values, are when the derivative equals 0. Right? And so the derivative equals 0, and that's where we're going to use this factored form, either when x is 0 or when x is 1. Okay? So at x equals 0 or x equals positive. Those are the zeros of this derivative here. Or you can just look at this graph here. Here's my derivative. A 0 is 0, and then this value right here, I bet you $1 million is 1, positive 1. Okay? So what I'm going to do now is I'm going to use those critical points to structure our what I would call analysis using the first derivative. So the way I like to do that is within a chart. Okay, so bear with me. I'm going to look at intervals of x, and I'm going to look at what the derivative is doing over those intervals, and therefore what my function y is doing. Remember, the whole goal is to analyze y, this original function up here. Where the heck is its min and max? Which, again, altogether is not a very difficult problem, especially if we were to use the calculator. But here's the calculus. Here's here's what we're getting paid the big bucks to think about. All right, so I have my two critical points at 0, so I'll put a 0 there and a 1 there. And what I'm going to do is I'm going to look to the left of 0. So in this area, when x is less than 0, I'm going to ask myself, what is the derivative doing? And note that the derivative over this interval is below the x-axis, therefore the derivative is negative, right? So if our derivative is negative, that means our function over that same interval will be doing what? That's right, decreasing. Right? So negative derivative corresponds to a decreasing function. Make sense? Okay, how about between 0, I'm going to look at the next interval now, between 0 and 1. And so here's 0, here's 1. Right, so I'm going to take a look at my derivative on that interval. So it's negative, and then it's still negative, right? So the derivative is negative almost everywhere, at least up until 1, except for at 0 and at 1, where it's 0, right? Negative derivative, still negative derivative until 1. So between 0 and 1, the derivative is still below the x-axis. Therefore, the derivative is giving us negative values, right? If we have negative values for the derivative, that means that the function is decreasing over that same interval, right? So right now, I know something that looks pretty obvious from the function. The function up until 0 decreases, stops, horizontal tangent, and then decreases some more. In fact, it's going to decrease all the way up until 1, right? Which up here is a 0 of the first derivative. This is the value of 1. That 0 corresponds to that particular valley, that minimum that we're looking for. And so after 1, my derivative, which is up here, here's 1, my derivative is positive. How do I know it's positive? It's above the x-axis. So what that tells us is after 1, the function will increase, right? And that's exactly what happens. So up until 1, it's negative, or at least from 0 to 1, and before 0. And then after 1, the derivative is positive. What that means, therefore, is that the function will increase. All right? So now let's think about what that means. What's happening on our function at these two critical points, at 0 for x and at 1 for x? Well, at 0, that's where the function changes from, At 0, that's where the function, the blue function, that's what we're analyzing, changes from decreasing, it stops momentarily at 0, and then decreases some more. Up until 0, after 0. So that's neither a max or a min. It is, however, a horizontal tangent, but it's not a max or min. The reason it's not a max or min is we don't have a difference, a change in behavior around that particular critical point. Right? We don't have, in other words, a change in sign, S-I-G-N, of the derivative, negative to negative, that happens at 0. Right? So that's an example of a critical point that's not a max or min, relative or otherwise. Okay? At 1, we have something interesting happening. At x equals 1, we have a change in the behavior of the function from decreasing to increasing, right? Or a change in the derivative from negative to positive. Right? And so you can see that the function decreases up until 1 and then increases. Right? So what's happening at 1? If that's where it changes a function from decreasing to increasing. That's right, that makes it a min. Right? So I now know for sure, which is something that was fairly obvious just by looking at the function, that at x equals 1 we have a minimum value. But just looking at something isn't very rigorous, right? Here's the calculus that supports that. Right? So to find our minimum value, all I know is at x is 1, there's a minimum value, right? Right? So how do I find it? That's right, I plug it back into the function, the original function that I'm trying to analyze, right? So I plug that one, bam, bam, back into the original function, and I get 3 times 1 to the 4th, 3, minus 4 times 1 cubed, 4, 3 minus 4 is 1. So here's the minimum value we're looking for, right? Which corresponds to this point right here. This would be the point 1, comma, negative 1, right? And that's the min, right? That's the minimum value. Right? Where do I find the maximum value of the blue function, which is what I'm analyzing, right? on the interval -1 to 2. Well, it's not here, right? It's not at 0, though we have a horizontal tangent. It's not a min or max. It's not here. It's not at that critical point of 1. That's a minimum we've already established. So where is it going to have to happen? No. Yes, it's got to happen at one of the endpoints, right? So it's going to either happen at x equals -1, which is somewhere around here, or at x equals +2, which is somewhere around here, right? So how do I tell where it happens? Right, I plug in -1 and 2 into the function, right? So where the heck is the max, right? We know there's a min here at -1. We can just look and tell. Here's a calculus that verifies, right? Here's my little chat. But what I want to know is where the heck the max is. I'm guaranteed there's got to be a min or max somewhere on this closed interval. It's not at either of the two critical points. 0, it's nothing. At 1, I have a minimum. So where's it got to be? The endpoints. So I'm going to plug the two endpoints, -1 and 2, into the function. And whichever one is higher is going to be my max, right? So the function is 3x to the 4th minus 4x cubed. So let's check the endpoints, right? What's happening at the left endpoint? Remember, we're given a closed interval to start with. So I'm going to check what's going on at -1. And then I'm going to check what's happening at 2. I have a sneaky suspicion that it's higher at 2, and that will be our max when x equals 2, but who knows? So let's plug a -1 in, right? I plug a -1 in here, right? And I get 3 times 1, which is 3, plus 4, which is 7, right? So 7 is the y value of this point somewhere up here as x, when x is -1, right? Let's see if what is happening at 2 is higher than 7, because if so, it will be the max. So when I plug in a 2, let's see, 2 to the 4th, 2 to the 4th is what? 2 cubed is 8, 2 to the 4th, 16. That's 32. 32 times 3, that's 96. I got to do this math out here. Minus 4 times 2 cubed. 2 cubed is 8 times 4 is 32. That's going to give me what? 6. Wow. 64. I hope my arithmetic is good. This time of the day, you never know. Right? So that's the y value way up here. Actually, we're out of the window range, and I don't know how to change it. Actually, well, let's see if this works with this. No. Let's see if we can. Oh, we're going to go that way. So I'm way over here, right? It's when x is 2. And we're well out of the range of the y values. But what I do know is the y value at 2 is 64, right? So here's a point 2, 64. Here's the point -1, 7, right? So -1, 7 to 64. What's the max? 64, that's right. So in conclusion, this function has a minimum here that I got from calculus, right? Right at this point, when x equals -1, the minimum was, that's right, -1. And then our maximum value, which we're sure to have a min and a max by the extreme value theorem, since this blue function is continuous on that closed interval, my maximum value is 64, which happens at way up here when x is 2. Okay, so that's how we can use calculus to find min and max values. Even though we can certainly do it on our calculators, this is the good stuff right here. Okay, come in with questions tomorrow. We'll do a couple more examples. Bye-bye.